Hi, and welcome to the new lecture in the Fun and Easy Machine Learning series. Today I'll be talking about linear regression. Linear regression attempts to model the relationship between two variables by fitting a linear equation to the observed data. One variable is considered to be an explanatory variable, while the other is considered to be a dependent variable. Please don't forget to subscribe and click the bell icon for more videos on machine learning. So the dependent variable, it's a variable whose values we want to explain or forecast. The independent or explanatory variable is a variable that explains the other variables, and the values are independent. Dependent variables can be denoted as y. So you can imagine a child always asking why is he dependent on his parents. And then you can imagine the x as your ex-boyfriend or girlfriend who is independent because they don't need you or depend on you. A good way of remembering it. Anyways, linear regression can be used in one of two ways: to establish if there's a relation between two variables, or see if there's a statistically significant relationship between the two variables. So for example, you want to see how an increase in sin tax has an effect on how many cigarette packs are consumed, how many sleep hours versus test scores, see what's the correlation between experience versus salaries, Pokemon versus urban density, and house floor area versus house price. The second application is to forecast new observations. We can use what we already know to forecast unobserved values. Here are some examples of the way that linear regression can be applied. So say the return on investment of fidget spinners over time, as well as stock price over time, or to predict the price of Bitcoin over time. So you can think of linear regression as the line of best fit. So the line of best fit can be represented by the linear equation y equals a plus bx, or y equals mx plus b, or y equals b subset 0 plus b subset 1 times x. You mostly learned this in school. So b is the intercept. If you increase this variable, the intercept moves up or down along the y-axis. And m is the slope or gradient. If you change this, then the line rotates along the intercept. So data is actually a series of x and y observations as shown on the scatter plot. They don't follow a straight line. However, they do follow a linear pattern, hence the term linear regression. Assuming that we already have the best fit line, we can calculate the error term epsilon, also known as the residual. And this is the term that we would like to minimize along all the points in the data series. So say we have our linear equation represented in statistical notation. The residual fits into our equation as shown: y equals b0 plus b1 times x plus epsilon. Okay, let's try doing this by hand in an example. Okay, so over here we have our dataset of Pokemon versus urban density. And this dataset you can get from my GitHub repository under range GT09 and machine learning FNE, which stands for fun and easy. Go to lab 1, linear regression, and then you will have the homework package that you can work on, and then as well as the solution. Over here on this site, you'll be able to find the same dataset as well as equations to finding the coefficients of A and B. And then to find the correlation coefficient squared, you can find that equation right over here. And you can just follow the address. Okay, so we have Pokemon, which is on our x-axis. Our y-axis is urban density. And then we can create a plot, a scatter plot of that. And then we can just format it to make it look a little bit nice. You can add in some data labels. And then we're gonna be calling this urban density on the y-axis. And then we're going to label this axis Pokemon quantity. Now remember, this is just a mock dataset. You can fill it with any data that you want, or you can import a legitimate dataset. Okay, so this is the equation that we get from our trend line, and we're going to create it on our own and calculate the coefficients by hand. So this is the equation that we have, and that over there is the sum of y. You can find it over there. Then you have the sum of x squared, which is over here, and the sum of x over there, and the sum of x times y. And n is the number of items in our dataset. So first we calculate x times y. And we can take 59 times 81, and this is our answer, and then we can just spread it across, and then we got our product of x and y. We can create the sum of that, so then that will give us sum of x times y. And then we can do the same for x squared, where you take the square root of 43. You can do the same for the rest of the dataset, and the same we can do for y. So we take y times itself, get 6561, and then we have the sum already. Now you can do the same for Pokemon, the sum of the Pokemon quantity as well as the urban density. That will give us the sum of each of our features. So we need to calculate our coefficients. So we have a, b, and r squared. So we can say equals, put in our brackets, and the first one is the sum of y and then you can enter the equation into the formula bar. I'm going to speed up this part of the video so it's not so monotonous. And then there you have it. We have 65, which is the same number that we get from our trend line. Now we can do the same for b. I've already done this before, so I'm just going to copy that and paste it there. You can do this by hand to get a feel for how to enter the equations. Let's see if you get the same thing. So it's quite simple. You just need to enter the equation as it is into Excel. And then you can do the same for r squared. As you can see, linear regression is very easy and simple. Okay, so in the next lecture, we're going to see how we can use this in Python using scikit-learn. See you in the next lecture. Please don't forget to like, subscribe, and share, as well as click the bell icon if you'd like to see more machine learning tutorials. And also please support us on Patreon. So see you in the next lecture.